Hello there, this is an Algebra 1 video. It is Chapter 7, Section 5, and today we are going to be exploring exponential functions. Now, an exponential function is completely different to what we've been doing in the past. We are used to seeing polynomials, we're used to seeing linear functions. Basically, we're used to seeing the variable in the bottom portion of an equation. For example, something like 2x squared plus 3 would be something that we would typically see. In other words, when we have a power, the variable is the base and the exponent is a number. So that's a normal situation, or I wouldn't say normal, because exponential functions aren't abnormal, they're just different. So I wanted to give you the formula, I guess, the form for an exponential function. And an exponential function is of the form y equals a times b to the x. Sometimes we can put the b in parentheses to kind of separate it from the a, because if you remember, PEMDAS tells us to do parentheses first, exponents, and then multiplication. So it would be totally wrong for us to go a times b and then raise it to a power. You need to take the b value, raise it to the x power, and whatever you get from that, you then multiply by a. So just want to be clear that this is a times b to the x. And then we have that a cannot equal 0. And hopefully that makes sense. If a was 0, then 0 times anything would be 0. And you wouldn't have an exponential function. It would all be 0. Another stipulation is that b has to be greater than 0. And again, if b was equal to 0, then you'd get 0 to some power. And again, you'd have that 0 situation. And of course, it can't be negative. And then we have b cannot equal 1. And b cannot equal 1 because, again, you would have 1 to a power, and 1 to any power is just 1. So all you would get is y equals 1. And again, that's not an exponential function. So here in pink, we do have some examples of what an exponential function would look like. It follows all of the requirements. We have y equals 2 times 3 to the x. You could have y equals just 4 to the x, or y equals 1/2 to the x. So all of these are examples of what an exponential function would be like, or what would qualify as an exponential function. So we're going to get busy with graphing. And it says here, graph y equals 3 to the x. Find the y-intercept and state the domain and range. The first thing I'm going to do is make a t-table. And whenever you're going to start graphing a function that you've never seen before, the best thing you can do is make a t-table and then just pick values so that you can kind of figure out what that function is going to look like. So I'm going to go ahead and pick a fair sampling of numbers. I want to pick negative numbers. I want to pick positive numbers, even some fractions. So these are the x values that I've chosen to use to graph my function. Again, you could pick any x values that you'd like as long as you pick negatives, positives, and 0. And so then I'm going to go ahead and say, what is 3 to the negative 2 power? Because that's basically what I'm trying to do here. I'm trying to evaluate the function when x is negative 2. So I need to figure out what is 3 to the negative power. We already learned before that that would be 1 over 3 squared. And we know that 3 squared is 9. So my answer would be 1/9. What is 3 to the negative 1 power? That would be 1 over 3, or 1/3. What is 3 to the 0 power? We learned already that anything to the 0 power is 1. And then we have 1/2. And we learned that when you have a rational exponent, this is the same thing as the square root of 3. And the square root of 3 is approximately 1.73. We know that 1/3 is approximately 0.33333 repeating. And 1/9 is approximately 0.111 repeating. So then we have the positive values. 3 to the 1 power is 3, and 3 squared is 9. So just like that, I'm going to erase this stuff here now, just so it doesn't clog my board. And now I want to graph these points. So negative 2 is roughly 0.1. So I have a graph here, and we have negative 2's over here. And I'm going by 2's here, 2, 4, 6, 8, 10. So -2, and then 0.1 is going to be really close down there. -1 is 1/3. So a little bit higher than that one, but not too much. And then we have 0, 1. And then we have, when x is 1/2, which is right here in the middle, it's going to be 1.73. Actually, I'm going to go ahead and fix something real quick here. I don't like my scale, so I'm going to go ahead and change it. And we're just going to go by ones, if that's okay with you. So this will be -1 down here, then 1, 2, 3, 4, 5, 6. And so then I'm going to go back and graph again. So again, -2 and 0.1 would still be really close here. -1 and 1/3 would be right about here. 0, 1 would be here. 1/2 is here, and then 1.73 is almost 2, but not quite. And then when x is 1, you go all the way to 3, so 1, 2, 3. And then at 2, it's going to be 9, so there's 6, 7, 8, 9. You can guess that it's about right there. And then we're going to connect our graph with a smooth curve. And that's what it looks like. And that is exactly what it's supposed to look like. Now, what you'll notice is find the y-intercept, and that's basically, they want you to find where the graph crosses the y-axis. Now, we kind of found the y-intercept by default because we used 0 here. But if you didn't know how to do that, and if you hadn't picked 0 in your table, then to find the y-intercept, this will never change. Doesn't matter what kind of function you have. The y-intercept you can always find by making x equal 0. Because there's no way that you're going to cross the y-axis unless your x-coordinate is 0. So, if we take y equals 3 to the 0, we already know that n to the 0 power is 1. So y would equal 1, so x is 0, y is 1, and that is your y-intercept. But we kind of already found it from our t-table. So our y-intercept is right here. And it says state the domain and range. Now for the domain of an exponential function, we know that domain is all reals. You can put any number that you'd like into the function. And so domain is all about what can go into the function without breaking the machine. For example, if the function was a square root function, we know that we can't take the square root of a negative number because it's imaginary. So that's kind of a domain issue. We'd have to say that you can't put in negative numbers. Negative numbers are not okay. But in this case, for the exponential function, it's okay to put in negative numbers. It's okay to put in positive numbers. And it's definitely okay to put in 0, as we already did, and got values. So the domain is anything, all reals. But for the range, when it's asking about the range, what it wants to know is what types of y values are possible. And so when you look at the graph, it's very easy to tell that this function is never going to go below the x-axis. So there's not going to be any y values that are below the x-axis. So that means that all of the y values are above the x-axis. So those y values would be 0, 1, 2, 3, so it would be 0 and up. So basically for my range, y greater than 0. In fact, it never actually equals 0. So we don't want to include 0 in our range. We want to just say that it's all the positive numbers. So basically all the numbers that are bigger than 0. And that is how you do example 1. So now we're going to have you do it yourself, number 1. And then we're going to go on to our next example. And this time, what the difference is between this one and the first one is that now our value here is something that is smaller than 1. So if you look back, our first one was 3 to the x power. But now we're going to be using 1/3. And we kind of want to see, just really quick here, notice how the graph is curving like this. Okay, keep that in mind because we're going to see something different happen when we use 1/3. But for the most part, we're going to do much the same thing, is create a t-table. And we're going to pick some values here. -2, -1, 0, 1, 2. Okay? And what's going to happen is you're going to put 1/3 to the negative 2 power. And we know that we can do this a couple of ways. We can distribute the negative exponent to both the top and the bottom. But when we have negative exponents, then we want to put the negatives on the top to make them positive, and the ones on the top to the bottom to make them positive. So you end up getting 9/1, or just 9. So when x is negative 2, y is 9. And then you plug in negative 1, and 1/3 to the negative 1 power. By the way, I don't know if you noticed this, but you can also change this to a positive if you reciprocate the inside. If you notice what happened at the end of the day is that we got this guy. This would be the exact same thing as 3/1 to the positive 2 power. So I reciprocate the inside and make this positive, and then this is 3 squared over 1 squared, which is 9. So it's the same thing. So I'm going to use that method for my second one. Instead of distributing the negative 1, I'm going to reciprocate the 1/3 and make that a positive, and then I'm going to get 3/1, or just 3. And that might be simpler. 0. Again, we know that if we put 1/3 to the 0 power, it's going to be 1. 1/3 to the 1 power is 1. 1/3 to the 1 power is itself, which is 1/3. And then we have 1/3 squared, which is basically 1 squared over 3 squared, or 1/9. So now I'm going to erase this stuff to give me some more space here. And again, we have found the y-intercept is 0, 1. And we're going to discuss the range in a bit. First, we're going to graph this little guy. So we have negative 2, 9. So here's negative 2, and here's 6, 7, 8, 9, maybe way up here. You remember that last time it was like on this side, it was 9. But now it's on the other side. Negative 1, 3, 1, 2, 3, 0, 1 is right there. That's my y-intercept. When x is 1, it's going to be 1/3, so right about here. And then 2, we know 1/9 is approximately 0.1, so that's going to be right there. And when you connect those little guys, you get a graph like that. So if you compare that to the one we did in example 1, you can see that all that really happened is it kind of flipped on the y-axis. That is a characteristic of when you have a number inside here that is less than 1. The other one was a 3, which is greater than 1. Not that they're going to ask you about that, but I just wanted to show you how cool that is, that it just kind of flipped it around. So the y-intercept, 0, 1. Our domain, again, all reals. Still have no issues with domain. The range is still going to be y greater than 0. Even though the graph has been flipped, we still don't have any y values down here, so we're still going from here on up. So y greater than 0. All right? So now we're going to go to an application problem, if you will. We have growth and decay. And in your book, you will notice on page 425, and you are welcome to enter this information into your notes. I did not put it on the board, but it basically goes through the what makes the graph flip. But I kind of already mentioned it earlier. Basically, if your A value is positive and your B value is greater than 1, so here my A value was 1. There is no number in front of the 3 to the x. So my A value is 1, which is greater than 0, and my B value, the base, is also greater than 1. And when that happens, you have a graph like this. The difference, by contrast, is this guy, where again the A value is still positive, but the B value, the 1/3, is actually smaller than 1. It still has to be bigger than 0, because that was the requirement from the beginning, but it's between 0 and 1. And when that happens, you have what we call exponential decay. This function starts off really big and gets smaller and smaller and smaller, whereas the other one started off really small and got bigger and bigger and bigger. That one's called exponential growth. This is an example of exponential decay. So we're going to do an application of that in example 3. And I got to warn you, Oh, sorry, this is your do-it-yourself question. And then here we have example 3. And in example 3, we're going to talk about soda. It says the function c equals 179 times 1.029 to the t power models the amount of soda consumed in the world, where c is the amount consumed in billions of liters, and t is the number of years since 2000. So in part A, it says graph the function. What values of c and t are meaningful in the context of the problem? We can graph the function for sure. We'll do that in a second. But before we get to that, what values of c and t are meaningful? Because this is a real life problem, it doesn't make sense for us to have values of t, of time, that are negative. So of course, we want to make sure that we mention that t needs to be greater than 0 or equal to 0. Because when t equals 0, that would be when we started. And that would be the 179 billion. So basically, if I let t be 0, then this to the 0 power is 1. And 1 times 179 is 179. So that means that when t is 0, so in the year 2000, there was 179 billion liters of soda consumed in the world. And as far as the c value, so we know that for the t values, we want them to be greater than 0. But in the context of this problem, c being greater than 179 is what we're looking at. All right, so now that we know that part, we're going to actually graph the function, and we're going to use the calculator to do that. So I am going to turn on my calculator screen here, and I hope that you can see it. I tried very hard to make this very visible for you. It is kind of complicated because of the projector, but hopefully we're going to black out my screen right now, making it a little bit easier for you to see the calculator screen. So there it goes. And so I want to show you how to graph this little function on the calculator. All right. So in order to do that, I need you guys to follow some steps. I'm going to try to write them over here on the board. One of the first things you want to do is locate the y equals button on your calculator. So you need the, let's put that back up there. Hold on, I lost my screen here. There's that. Okay. Well, I thought I would be able to write on this, but apparently I can't write on top of it. But that's okay. So a couple of things that I want to just be clear is that you want to pick, you want to use your, so pay attention to what I'm saying to you, because I can't write on the screen, so you have to listen very closely. You want to find your y equals button, and your y equals button is at the very top row of your calculator. So we hit the y equals button. And I will tell you right now that if any of the, you can see that it says plot 1, plot 2, plot 3. If any of those plots are darkened with a box, kind of like what you see right now, the plot 1 is darkened. If you see something like that, then you need to take it off. Your calculator will not graph accurately when those plots are on. So to turn them off, you use your arrow keys, which are right here, to get yourself up there where it's blinking. And then once it's up there blinking, you hit enter and it will turn it off. So you want to make sure that that's definitely off. You want to make sure that none of your Y1s have anything in them. So you can see that mine are all blank. If yours are not blank, just keep going all the way down. And if there's anything written in them, you want to clear it all out. So here I am in my Y1, it's all cleared. I want you to type in the 179 and then hit the times the multiplication button. Use your parentheses and then put 1.029, close the parentheses, and then to do the power button, you want to use the caret key, which is right here below the clear button. It's like a little, it looks like almost like a little arrow going up, so that's called the caret key, and that means to raise to the power of the variable, and you have a variable button, and it's right here next to the alpha button. And it says x, t, theta, n. And basically what that means is that it's just a generic variable button. So even though we have a t in the problem, it's going to show up as an x. But basically the x doesn't really matter what you call it as long as it's a variable. So we're going to use x, and so you should have 179 times 1.029 to the x power, hit enter. And then you want to go to your graph. And if your graph is anything like mine, you're going to go zoom, which is again at the very top row of your calculator. It's the third button over. You hit zoom and go to option 6, which is what I have. That's going to give you a standard window of -10 to +10, -10 to +10. But as you can see, like my calculator, when you graph this, you probably didn't see anything. There's nothing on your screen. The reason why you don't see anything is because the number 179 is really huge. And so all we can see here is from like -10 to +10. So 179 is way up there somewhere. So what we have to do is adjust our window. So I'm going to tell you right now, what you want to do is go back to the window button. And so you should have a screen like this when you find the window button. And I need you to realize that this x-min just means what do you want the smallest x coordinate to be? The biggest x coordinate. What is your scale? Like, do you want to go 2, 4, 6, 8? Or do you want to go 10, 20, 30, 40? And then you have something for the y-min, y-max, y-scale. The x resolution, just leave it at 1. So I'm going to tell you that for the x, we're going to go -50 to +50. So we're going to type in -50, enter, +50, enter. And for our scale, we're going to go by 10. Which means we're going to go 10, 20, 30, 40, 50. For our y minimum, we're going to go from 0 to 350. Now remember, we don't want to use any negatives for the y because it doesn't make any sense for us to have negative values if we're talking about billions of liters of soda consumed. So 0, we're going to go all the way to 350. And this time, because the numbers are so big, we're going to use our scale to be 25. So we'll go 25, 50, 75, 100. So once we do that, now we can hit graph again. And again, your graph button is the very last button at the top row here. Hit graph, and this time you should actually see the graph. It was always there, we just didn't have the right window to be able to see it. Okay, so that is how you graph, and that's the first part of part A. And now they want us to find out how much soda was consumed in 2005. So I'm going to go ahead and turn off my screen now that we've done the calculator portion of it. And then we will go back to our whiteboard, hopefully, if all works well. And here we are. It says how much soda was consumed in 2005. Now remember that originally T is the number of years since 2000. That means that the year 0 represents the year 2000. So 2005 would be T equals 5. So all we're going to do is evaluate the function when T is 5. So my function is C equals 179 times 1.029 to the 5th power. So instead of a T, I'm going to replace it with 5 for 2005. And remember what I said earlier, when you're evaluating an exponential function, you want to make sure that you do exponents first. So I'm not going to go 179 times 1.02, that's be wrong. I'm going to take and do 1.029 to the 5th power. And again, remember the 5th power, you want to use your little caret key. So I'm going to raise that to the 5th power. And I get 1.1537. Okay? Now I'm going to take that answer and multiply it by 179. So in the end, I get 206.505. Okay? So how much soda was consumed in 2005? Roughly 206.5 billion liters. That is a lot of soda, kids. Please stop drinking so much soda. All right, so now here we go in do-it-yourself number 3. Now, lucky for you, they didn't actually ask you to graph this one. They're just asking you to answer that question there. So you will do that. And then we'll go to our last example here, and it says, determine whether the set of data shown below displays exponential behavior. Write yes or no, explain why or why not. Very easy test for us to see if there's exponential behavior or not. And that's to kind of find that common ratio, the b to the x powered part. So what you can do is you can take your values here and see if you have a common ratio. And so what you can do is take 32 and divide it by 64, which gives you 1/2. 16 divided by 32 also gives you 1/2. 8 divided by 16 gives you 1/2. 4 divided by 8 gives you 1/2. And of course, 2 divided by 4 is 1/2. So because they all have that same common factor, then most likely this is going to be exponential behavior. You can confirm that if you graph the points and if you see that smooth curve. I'm not going to do that right now in the interest of time, but this is pretty much going to indicate that you are going to have exponential. So the answer here would be yes. So you can do something very similar with do-it-yourself number 4. And once you have done that, you will have completed your notes for this lesson. And I will see you in class, and thank you for watching.